So for our example of the effect of light pressure, let's consider an asteroid. So we've got the sun shining here, and we got an asteroid out here. And let's say our asteroid, to make the math easy, let's say the asteroid is perfectly circular and has a diameter of 1.24 kilometers. And it's at such a distance from the sun that the intensity of the sunlight here, and again, the pointing vector measures the intensity of sunlight. The intensity of sunlight here is going to be 1.21 kilowatts per square meter. Okay, so the question is, how hard does that light, what's the force on that asteroid of that light? Now, this actually turns out to be an interesting thing, because as the asteroid is orbiting around the sun, this is one thing we worry about if the asteroid's orbit crosses the orbit of Earth somewhere. And so we can calculate where the asteroid's going to be as long as it follows its orbit. But because the sunlight is pushing on the asteroid's orbit will very slowly over time shift. And so an asteroid that may look like it's going to safely miss Earth might actually be pushed into Earth. Or an asteroid that looks like it's on collision course with Earth, hundreds of years in the future, might actually miss us because the sunlight pushes on it. And so this turns out to be something that is of actual concern. We monitor asteroids. So we want to know, how hard does the asteroid push? Or rather, how hard does the sun push on that asteroid? So we know that there's a formula for the pressure here. Now, the pressure is 1 over c times the pointing vector, or the pressure is equal to 2 over c times the pointing vector magnitude. This is the formula. We just derived that if we have absorption. So the light is absorbed. This is what we get if we get reflection. Okay, now we need to know one other thing about the asteroid. How reflective is it? So we're going to assume our asteroid has an albedo of 0.12. Now, albedo is the reflectivity. So an albedo of 0.12 means it reflects 12% of the light that hits it. The rest of that light, 88%, is absorbed. All right. So 12%, 0.12 albedo means 12% reflects, 88% absorbed. So that means the pressure on the asteroid is going to be 0.12 reflected. So 0.12 times 2 over CS. And it means it's going to be 88%, so 0.88, 1 over c times s. So you work that out, and that comes out to be 1.12 s over c. So that's going to be equal to 1.12 times the intensity of the sunlight here, we said was 1.21 kilowatts per square meter. So that's 1,210 watts per square meter. Remember, we have to watch our units. If we don't get our units right, then the calculations are going to be wrong. Okay, divided by 3 times 10 to the 8th meters per second. And so the pressure comes out to be equal to 4.52 times 10 to the minus 6 Newton per meter squared. A Newton per meter squared, if you remember from Physics 1, is a Pascal, a unit of pressure. So now we have pressure, but I asked for the force. How hard do you push on the asteroid? Well, that's easy. Again, think back to Physics 1. Physics 1 told you that pressure was force per area. So that means the force is just going to be pressure times area. So we got this asteroid here. It's a spherical asteroid. The light's hitting it. So we want the cross-sectional area. So the cross-sectional area is pi r squared. Okay. Well, we know the diameter was 1.24 kilometers. So that means r is going to be 0.62 kilometers. Okay. So the force is going to be the pressure times pi r squared. So the force is going to be the pressure, 4.52 times 10 to the minus 6 Pascal, which is Newton per meter squared, times pi times 0.62 kilometers is 620 meters squared. So the force comes out to be 5.46 newtons. Now that's not a whole lot, for something as big as an asteroid. But remember, this is 5.46 newtons. Nothing else is balancing this. So you have 5.46 newtons pushing on it 24 hours a day, 7 days a week, 365 days a year, continually. As long as it's in the solar system, the sun's pushing on it with that little bit. That little bit within that tiny little push, as big as the solar system is, that tiny little push changes the orbit by a tiny little bit, while a tiny percentage of the orbit can move the asteroid for thousands or tens of thousands or hundreds of thousands of miles over time. And so this is actually one of the interesting things that they are discussing with, for example, if you see an asteroid heading towards Earth, what do you do? So you got Earth and you got an asteroid, and you know its own collision course with Earth. Now, in science fiction, in Hollywood, it's real simple. You just send a spacecraft up here and blow it up. Or you send nuclear missiles at it and blow it up. In reality, it doesn't work that way. First of all, these asteroids are pretty tough, possibly. Secondly, even if you blow it apart, then your best case scenario is now you have a whole bunch of little ones slamming into Earth. Okay, but if you blow it apart, there's nothing else out there pulling on it, so these parts will actually come back together and reassemble the asteroid. It's a big pile of stuff, and now it's still coming at you. And so what do? Well, one possible strategy is change the albedo. And you think about it, so what does that do? Well, if you change the albedo, you're going to change the force on it. If you change the force on it, the sun is going to push on it a little bit differently than it was before, and now the orbit could actually miss Earth. And so that's one strategy. Now, by changing albedo, you just have to paint it something more reflective or less reflective. If it's very shiny, you might want to change the albedo by making it darker, absorb more light. If it's dark, you might want to make the albedo different by painting it with something light. Now, I don't mean you send a bunch of astronauts to the asteroid with a bunch of roller brushes and they paint the thing. You could send a small unmanned spacecraft that has a nose cone that is full of like chalk powder, like white powder or silver powder or something that you spray all over the asteroid, and that would change the color of it, and so that would change the reflectivity of it, and then the sunlight would simply push harder on it, and that would change the orbit. So that's one simple strategy for deflecting an asteroid using this idea of light pressure.